Let's have a quick glance over our understanding of learning in machines. The machine is exposed to examples and is required to generalize the understanding. For instance, identifying handwritten numbers. Based on provided examples, the machine is able to provide predictions on unseen data. Let's see another example. Consider we are working with a model that predicts if a fruit is poisonous based on its color. The model sees a few examples and then makes its own predictions based on what it learns. To formalize, consider the sample set S of size M taken from a distribution D. Let's say f is the true labeling function. The machine's goal is to predict the function or get as close to it as possible. We will call this predicted function a hypothesis. Now, how do we find a good hypothesis? For that, let's define a loss of a hypothesis, which gives us the probability that for a chosen x, which is a sample point, we will have a mismatch between the true labeling function and our hypothesis. And our goal shall then be to reduce this error. However, there's a small problem. We just have the sample and don't know anything about the underlying distribution, nor anything about the true labeling function. What we can, however, do is consider a modified loss function. In simple terms, the fraction of the mismatches in the sample. We will call this the training error. Now, the goal of the model is to look for a hypothesis that minimizes this error for this specific sample. This method is called empirical risk minimization. Now, there's one more catch. Consider this example. A hypothesis that assigns the poisonous tag to only the known examples and calls any other fruit non-poisonous. Which means the poisonous fruits are assigned poisonous if it belongs to the sample, otherwise it's just non-poisonous. This, despite working perfectly for the sample, has terrible performance on unseen data. We call this overfitting. To fix this issue, we will restrict the search of hypothesis to a specific set of functions only, calling it the hypothesis class. If this class is chosen appropriately, then a hypothesis that performs well on a training sample is likely to perform well on the underlying distribution as well. The goal is now to look for a hypothesis function that minimizes the training loss. This restriction is also called inductive bias. A simple restriction is considering a finite hypothesis class. For instance, all predictors that can be coded in C++ of a certain length only. We'll now have a look on how the empirical risk minimization, or the ERM, works on this hypothesis class. But before that, we will make a few assumptions for now. The first one being existence of a true labeling function. In other words, the one with a loss equal to 0 over the distribution and is within the hypothesis class. We call this the realizability assumption. Another assumption shall be the independent and identical distribution of all the samples, which simply means that the samples follow the same distribution and are all independent of each other. We will say that a learner has performed well if its loss over the distribution is less than a fixed epsilon, and call it a failure if the loss is greater than that epsilon. Therefore, we are interested in samples which lead to a failure. We'll try to have an upper bound on the probability of getting such samples. Now, let's define a set of bad hypothesis classes which has error greater than epsilon over the distribution. Further, a set of misleading samples where there exists some h in the set of bad hypothesis class whose training error is 0. The ERM outputs a hypothesis that has a training error equal to 0 under the realizability assumption. But it belongs to a set of bad hypothesis class. In other words, the ones with bad overall performance. Now let's get back to this set. The set of samples leading to a bad overall performance. Notice that it's a subset of the set M. Note that HS is the output of ERM, hence the training error is 0 and it further has a bad overall performance. Hence it's a subset of the set M. Great. Now take a look at this set. Notice how we can write it as a union of samples on which a specific bad hypothesis has training error 0. We will just go over all the bad hypotheses and then we can take the union of those samples and we will have the set M. Now getting back to this relation, we can claim the following. Now expanding M, just as we had discussed, probability of unions is less than or equal to the summation of probabilities. Hence we can write this. The probability can be rewritten since it's for each sample and the samples are independent and identically distributed. We can write it in the product form. The probability is simply 1 minus the total loss. The total loss being greater than epsilon for a bad hypothesis. We'll have the following. Simplifying, we'll have this. Now HB is smaller than the full hypothesis class. Recall that it's finite and using a simple inequality we'll have the final expression, which is the upper bound of the required probability. Note that increasing the size of the sample, which is M, the upper bound decreases, which means the samples of bigger size will result in ERM giving us a good hypothesis with high probability. In the next video, we will visit a corollary of this idea, which forms one of the most fundamental ideas in learning theory.